this is the 12th lecture in the series, and this lecture we will prove Buchberger theorem. So this was a theorem that we mentioned in the last lecture. So I is an ideal in the polynomial ring in n variables over a field K, no assumption on K other than that it's a field, and G is a generating set. G is a generating set, some elements, G1 through Gm. Then G is a Grosvenor basis precisely when for every pair I and J, the remainder of the S pair Gi Gj, when we divide this by elements of G in any order of elements of G, the remainder is 0. Okay, so this is a characterization of something being a Grosvenor basis for I. Okay. So now let's prove this statement. Okay. So one direction is more straightforward than the other, in fact quite straightforward. So this is the direction. So assume that G is a Grosvenor basis. Then so let's let I be different from J, and let F be the S pair of Gi Gj. Okay. Recall from the definition of Gi Gj, S Gi Gj, first you multiply Gi by some monomial, then you multiply Gj by some monomial, and then you take the difference to remove the leading term. So this is inside I. But then we saw that so if F is inside I, when we divide F by elements of G, because G is a Grosvenor basis, we know that the remainder of G in the order will not depend on the order in which we divide, or it's completely independent of what the coefficients of the G's are. The remainder is independent, and F is inside I means that the remainder of this is the characterization of F being inside I. Okay. So this is the proof in one direction. It's just an old result about which we proved many lectures ago, that G, if something is a Grosvenor basis, then the remainder is a well-defined quantity, irrespective of the order, etc. And an element is inside I precisely when the remainder is 0. So this is the easy direction of that theorem. Now in the other direction, one needs to prove that it is a Grosvenor basis. So it will take some, one will have to prove that for any F, in F is divisible by in Gj for some J. Okay, that's what it makes it a Grosvenor basis. Okay. So this is this direction. Okay. So now by way of contradiction, okay, assume that G is not a Grosvenor basis. Therefore, there exists some F in I, not 0, such that in F is not in the ideal generated by in Gi 1 less than I less than M. remember that G1 through Gm was the, what the set G is. So the initial terms of them do not generate the initial ideal. That's what we are assuming. So there is an F with this property. Okay. So now let's choose. Okay. So now we want to make some choice about F, and we will prove that F with some property, and we will prove that there is a contradiction there. Okay. Among so this is important that among all such F and all such expressions F as an R linear combination of the GI M. Okay. Remember, F is the set G generates the ideal. That's the hypothesis, and then we are assuming that, but it is not a Grosvenor basis. Okay. So F can be written in terms of the GIs, but in F cannot be written in terms of the in GIs. That's this hypothesis. So among all such F and all such thing, choose one such that in choose one such that in of HIGI choose one such that the maximum of the in H1 G1 in H2 G2 in HM GM is smallest. Okay. Call this value mu. Okay, let's go back and say what this means, what is being said. So there is some F with this property. Okay. F itself can be written like this. Now, among all such F with such that this is true, such that this among all such F with this where this is true, and all such expressions where F is written as a linear combination of the GIs, choose one. So for any such expression, compute this maximum of the initial terms of the individual terms in the sum, HIGI. Choose one that is smallest and call that smallest value mu. Okay, so that's one thing. And next reduction is among all such expressions as above, okay, such expressions in some HIGI, okay, as above, choose the one, okay, such that now, it is possible that many of the, for many I, HIG, the in of HIGI is equal to mu. Okay? So choose the one in which such that the set of I such that in HIGI is equal to mu is minimum. Okay? So the idea of the proof would be, given such an F and such an expression HIGI, which also determines mu and this number, there is a different element in which either this cardinality of the set, the size of the set is minimum. Either this set becomes smaller or m becomes smaller. Okay. Either way, we have contradicted the choices, and that will be the end of the proof. Okay. So this is a little complicated induction, but we will do that. Okay. So first observe that mu occurs at least twice as in HIGI, because before we observe this thing, we need one more observation about in F and in these things. Sorry, what is? Yeah. Okay. So, what is the relation between the maximum of in HIGI and F? Okay. So, the sum HIGI gives F. So, the maximum here is less than or equal to the maximum of the initial term here is less than or equal to the maximum of the initial terms of the sum. There may be cancellations, but the initial term of this cannot be greater than the initial term of every one of these things. Okay, so that's, and that maximum is m. So F is less than or equal to m. That's sort of by definition. But we can say more. F is less than or equal to mu. That initial term here is mu. So it's less. The max of this is mu. So it's F is less than or equal to that. But we can say more, because if F is but mu is divisible by in Gi for some I, but in F is not. The assumption was in F is not in the initial ideal, so it's not divisible by the initial terms of the elements of the generator of those G. Okay. So this now implies that F is strictly smaller than mu. In F, I'm sorry, this should say in F is strictly smaller than mu. Okay. So now let's observe that mu occurs at least twice in the set, I mean the collection in H1 G1 up to in HM GM. Why? If it appeared only once, then it would not get, let's say it appeared only for H1 G1. So the initial term of H1 G1 is mu, everything else here is smaller, which means the sum will have initial term H1 mu1. Which is the same thing as H1, initial term of H1 G1, which is mu, but that is the initial term of F also, but that we know is not true, since initial term of the sum of HIGI, which is F, remember this is F, is less than mu. So the initial terms of at least two of these things should get cancelled before we get F. Okay, so let's make this observation. Okay. So again, therefore, without loss of generality, we can rearrange these terms and assume that H1 G1 and H2 G2 have the same initial term mu. Okay. So now let's okay. So note that the LCM. So note that the initial term of G1 divides mu. Initial term of two polynomials is the product. Initial term of the product of two polynomials is the product of their initial terms. So the initial term of G1 divides mu, similarly initial term of G2 divides mu, hence the LCM of the initial terms divides mu. Okay. So we can write this, so let n be a monomial, be the monomial, such that n times the LCM of the equals mu. Okay. So this is okay. So now we need to study the S pair. Okay. So we just need to introduce some notation because we have to keep using this this thing. So let L1 be the LCM of in G1 in G2 divided by in G1, similarly L2. Where you divide by G2. Okay. So then notice that S of G1 G2 is now L1 G1 minus L2 G2. Okay. Now let's look at various initial terms now. Okay. The n times the initial term of S of G1 G2, this is going to be less than n times the initial term of the we just need n times the LCM. So remember L1 G1 the initial term is the LCM, L2 J2 the initial term is is also the LCM. The difference leading term will be strictly smaller of initial term of G1, initial term of G2. So that is just this expression was constructed precisely to cancel their respective leading terms, both of which have this value, and this was mu. Right? N times the n was chosen such that this is equal to mu. Okay, so we would need to use this later. Okay, so by assumption, okay, so the assumption was let's we'll come back. Let's just write. So notice that the S pair is an element in the ideal, so it can be written as some PIGI. Okay. Its initial term is strictly less than mu, hence how was mu chosen? It was the among all such elements whose initial term is not inside the ideal generated by the initial terms of the GI, choose an expression of this form such that this is smallest and its value is mu. But now we have an expression like this whose initial term is strictly less than mu. So in other words, it says that, so therefore we may assume that, okay, so we may assume by assumption on mu, okay, we may assume that we see that the initial term of S of G1 G2, okay, is equal to the max of in P1 G1 in P2 G2, P2 times G2 and so on in PM GM. If this were not the max, then this expression would also satisfy the condition which was used to pick out mu, but then the initial term of this is strictly less than mu. That would have contradicted the choice of mu. So one can choose with this property. Okay. So now with this we can rewrite f as some HIGI plus n times SGI G1 G2 minus n times some PI GI. That is just saying, I mean, we have just added something and subtracted the same thing. So that's not, it's not changing the value. Okay. Now in this expression, notice that the maximum of the initial term, so we can rewrite it like this. So in this expression, there is a G1 and a G2 appearing in the definition of S. Then there is something here. So in this expression, there is in this expression, it does not change the number of times mu occurs as the initial term of these the terms inside here. Nor does it affect the fact that m is the maximum of the initial terms on the right side. Okay. So therefore, let me just summarize that thing. Okay. So this does not affect the maximality of m or the number of its occurrences. Okay, in this collection. Okay, so we have not removed any of the leading terms for which it is m. Okay, so now using this we can rewrite f now as. Okay, so let me G1 times H1 plus NL1. So this is just this would be L1 G1. So I'm just calling that NL1 plus minus NP1. Okay, that's just collecting the G1 terms plus G2 times H2 minus NL2. So one would have a minus L2 G2 here and then a multiplication by NP2 and then plus plus I goes from 3 to m Hi minus NPI GI. Now let's look at consider in of G2 minus NL2 minus NP2. This is the, sorry, not G2, H2. Okay. This is the coefficient of G2 in this new expression. Okay. Let's look at the initial terms. We are not, we want the initial term of this times G2. Okay. In of H2 G2 was mu. There was this is not m but mu. So this was mu. In of n, G2, P2, this is less than or equal to the max. So here, notice P2 G2 is less than or equal to the maximum of the initial ideal of the S pair, which itself is less than mu. Where was that? It was right. So this is less than mu. Okay. And the important point is in of n L2 G2. Okay, this is n times, this was LCM of in G1 in G2 divided by in G1 in G2 times the initial term of G2. So these two cancel, and this is equal to n times the LCM, but the definition of n was that it is equal, this product is equal to mu. Okay. So in other words, what the conclusion for us is that in of H2 minus NL2 minus NP2 G2 is less than mu. Okay. This contradicts the minimality of, okay. So this contradicts, remember mu was chosen with certain properties, and this contradicts one of those properties. Among such expressions, the number of times in which this occurs is minimum. Okay. So previously we had assumed that H1 G1, H2 G2 and possibly other things all had the same initial term mu, out of which we have removed one term, which is we have changed the coefficient of G2 so that with the new H2 in of new H2 times G2 is strictly less than mu, so this contradicts the minimum. Choice is made earlier. Okay. And hence, therefore, the conclusion is there, and all of this came by assuming that there is an F. So conclusion is that in F is inside the ideal generated by in G inside G. Okay. In other words, G is a Grobner basis. For I. Okay, so that's the end of this proof. So now I just want to show one example in. Okay, so these lines which follow a 2% sign Macaulay 2 and offset from the left like this. This is this is the Macaulay code that we enter, and this is the output of various lines that just sequentially given. So in the first line we just defined a ring, and then next line we defined an ideal, and notice the new way in which we have defined ideals. So we have just written like a string, we have written x5 plus y3 plus z2 minus 1. It will understand it as x to the 5th plus y cube plus z square minus 1. It's a convenient way of entering polynomials into Macaulay 2 if the variables don't have subscripts. If the variables have subscripts, we cannot do it. We have to do it the way we were doing it till now. Okay, like x caret 5, etc., etc. Okay, so this is a convenient way of doing that. So these three lines are corresponding out. So we ask to compute the Grobner basis of I. So this is defined in the GLEX order, and we just call that thing GBI. This is just a name. Okay, this is the thing, and it says it's a Grobner basis. The status of it is done, and S pairs encountered up to degree 5. So it kept computing and it went up to some degree, some large degree. And let's look at the elements of the Grosvenor basis. So we continue the calculation. So this is, we're asking for the generators of the Grosvenor basis, meaning the actual elements of the Grosvenor basis. So it outputs something, y cube plus x square plus z minus 1, which is one of the generators. Y cube plus x square plus z minus 1. Remember, this is g-lex, so this is the that is the leading term. Okay. Yeah. So then, okay. So we now continue. So the complexity of computing a Grosvenor basis depends heavily on the monomial order that we choose. So we just repeat the same thing. So here we got something. So now we ask same thing. We just redo all the calculations, but now the ring is defined with monomial order lex. Okay, and the same ideal, and we ask to compute Grosvenor basis. Suddenly we notice that S pairs encountered up to degree 86. There, previously it was just 5. Okay, so there's substantial difference in the complexity between lex and g-lex. Yeah, so now we ask to show the output, and it is so big that it is just, there are 86. So here this is degree 79. It starts with 79, z to the 78, z to the 77. Okay, so with some very long, there are 7 generators first of all in that thing, and it's just a very long. So this is the end of this lecture. In the next lecture, we will look at quotient rings and how Grosvenor basis comes in handy to study them. And we'll also, using the same idea, we will also come up with a criterion to decide if some system of polynomial equations has finitely many solutions.